Right. So thank you very much. It's a great pleasure being here. It's a great honor to speak here. And the IIS is a wonderful place for work, actually. So I'm going to tell you about what I'm doing here in the Institute. It's mostly work in progress, but I will also be very simplistic in the beginning. So my apologies to everybody who is quite familiar with symplectic geometry. I will be fairly simple in the beginning. So the question which I try to answer or give a possible answer is a fairly simple question. So anybody who remembers if he had a course in classical mechanics, was in math or in physics, remembers that Poincaré recurrence in classical mechanics in the transition to statistical mechanics was derived from classical mechanics, canonical transformations, and from this one feature of volume preservations called the theorem of Liouville. And this volume preservation is derived from the fact in classical mechanics that you have a symplectic transformation. Usually that term is not used in physics, symplectic transformation. So once you have volume preservation, you immediately get Poincaré recurrence, a very important feature, sort of a fundamental feature from which then you start statistical mechanics. But the question which should arise is, okay, where does the symplectic feature from the original classical mechanics then stay? Is it just about volume preservation? Where is the symplectic geometry left? So I'm trying to follow this question, and I'm attempting to give a possible answer. So, I will spend almost the entire first half sort of introducing symplectic geometry. And so where does symplectic geometry arise from? So let's say Q is the n-dimensional configuration space from physics. So for example, n could be 3n if we have n particles. It's the space of positions. So, so for classical mechanics, however, it's not just important to have the configuration space. If you want to formulate the equation of motions in the Hamiltonian picture, we have to go to phase space. So what is phase space? Physical phase space, mathematically speaking, is you take the configuration space and you associate to each position variable the conjugate momentum variable. So this is, mathematically speaking, the cotangent bundle. So the cotangent bundle means our momentum variables are elements in each cotangent fiber where Q is a point in the configuration space. So dimension of the cotangent bundle now is 2n. It's even dimensional. All right, so if we want to do physics, then what we study then on this phase space is the Hamiltonian function. And the Hamiltonian function in classical mechanics is usually the sum of the kinetic energy and potential energy. Kinetic energy, for example, is the sum of the kinetic energies of each particle, and the potential, which is a function only on the configuration space, captures the interaction between those particles. Once we have the Hamiltonian function, equation of motion is the Hamiltonian equation. So the Hamiltonian equation now in these coordinates, q1 to qn, p1 to pn, can be formulated as follows. If q is the entire q vector, q dot equals the gradient only in the p variable, dh dp, p dot equals minus dH dq. So this Hamiltonian equation is completely equivalent to the Newtonian equation. This is an ordinary differential equation of first order. And by going to the phase space, we have it first order. If we would formulate it in the Newtonian way, we would have an equation of second order on the configuration space. So that's this Legendre duality. So here we have the Hamiltonian form. So in this Hamiltonian form, we have two fundamental laws of conservation. The first is energy conservation. Which simply means that the total energy, the Hamiltonian along orbits, is preserved. That's mathematically very easy to see. If we derive the Hamiltonian function along an orbit, which is a solution of this ordinary differential equation, then simply by chain rule, this is dH dq, q dot plus dH dp, p dot, this is 0. You just see it here, the minus sign is the essential part. So what is the second law of conservation? The second law of conservation, this will be the invariance of the phase space geometry. And this is exactly where symplectic geometry arises. So in order to describe this, so now let's first define symplectic geometry. So now in a more abstract term, a two n-dimensional manifold, think of phase space, for example, cotangent bundle, is a symplectic manifold. If we have a differential two form which is closed and non-degenerate. So the non-degeneracy means we can use it to identify vectors with covectors, tangent bundle with cotangent bundle. If we take a tangent vector and we plug it into this two form, then non-degeneracy means that this is an isomorphism. So we can turn vector fields into one forms, back, forward, and backward. So what kind of symplectic manifolds do we know? So the standard space is R2n, which we could view exactly as the cotangent bundle of Rn. And if we take our standard variables, then the standard symplectic two form is just summing up dqi wedge dpi. So how can we get some idea of what such a closed two form is? So one way to picture this two form is to think of it as a form of oriented area computation. So we could take a closed curve, in our symplectic manifold. Let's take R2n. It's just a local description now. And suppose sigma is a disk spanned by gamma. Then we would like to see what the integral of this two form over sigma is. And one way to understand it is project in n many different directions from this symplectic space into the two-dimensional planes. Here it is important that the two-dimensional planes are spanned by the two conjugate variables, qi and pi. So we think now of R2n to be the n-fold product of R2 cross R2 cross R2. If we project the closed curve into that plane, so here's our two-dimensional plane, we will have some maybe intersecting curve, gamma I, and now we compute in the Euclidean area form the oriented surface. So this is important that we think of the oriented surface. So we give the curve some orientation, and we look at each surrounded piece of area, and we compute this area with sign. So the area in particular could also be 0 if it's figure 8 and two area sizes. And that gives us some area AI. And this expression is simply summing up those areas. So of course, mathematically, you could also see this much simpler just by Stokes. This symplectic form is the differential of some one form, for example, summing up p dq or q dp, and it's simply the integral of lambda along this closed curve. All right. Okay, let's go back. Let's take this statement. Now let's go back to invariance of phase-space geometry. So if we have our Hamiltonian function, then one way, so the coordinate-free way to describe this ordinary differential equation, this is where the dynamics come from, would be to say we take the differential of h using the non-degeneracy of the two form. We translate this one form into a vector field, and this vector field is exactly in our symplectic coordinates dh dp ddq minus dh dq ddp. So in particular now, this vector field will generate a Hamiltonian flow. And if we now take this flow and we ask, how does this flow transform the given geometric structure, the two form omega? Deriving this along the flow means applying the Lie derivative using Cartan's formula, which is the symmetrized combination of exterior differential with contraction of the Hamiltonian vector field to omega, is now using that omega by assumption is closed. This term gets kicked away. Contraction of the vector field into omega is dh. So this is twice the exterior differential on h, and this is 0. Okay, so this is what we mean by invariance of phase-space geometry. So we see we have a two form which is closed and which is invariant under this flow. So note that the non-degeneracy of omega, the way we define this, is equivalent to saying that if we take the maximal alternate power, the n-fold alternate power of the two form, that gives us a 2n form. And if we do this and we normalize by n factorial, so this gives a volume form on M, which is just the classical standard volume form on R2n. So in particular, this symplectic invariance tells us we have a volume-preserving flow. So this is where we'll come back in a moment. So there's one thing I want to deal today a lot with, is a kind of a particular type of invariant subsets. So let's go back for that to physics again. So a major part where all this study of dynamical systems was sort of began with was celestial mechanics. And in celestial mechanics, usually there is one structure derived from the symplectic structure used a lot for the techniques, and that's the so-called Poisson structure. The Poisson structure is a Lie algebra structure. Lie algebra structure on the ring of smooth functions. Yeah, so this now turns it into a non-commutative structure, and this Lie algebra structure is simply defined by associate to each function the associated Hamiltonian vector field, where this identity, and then just take this antisymmetric product of these two vector fields. Clearly, this is a derivative on each function. And it's not entirely obvious, but it's an easy exercise to prove the Jacobi identity. Yeah.
So I'm trying to understand, if I were a physicist, which I'm not, are you saying that I would have a Hamiltonian? Is like a symplectic form the only kind of two-form that's invariant under this flow?
Oh no, certainly not. I mean, you can do a lot of ad hoc constructions sometimes, but if you do not make any further assumptions, I wouldn't know of any other a priori conserved quantity. You might have some more special geometric conditions.
So are you saying if I was a physicist and I had Hamiltonian and I cared about it, this is the only canonical invariant?
As far as I know, yes. Yeah. Right.
So usually there's no.
Yeah. But I'm already, so I'm the whole talk is simply about understanding the difference between the preservation of the volume form, which we can derive from this, yeah, and all these dynamical features like Poincaré recurrence, and asking, well, what if we use this origin, this much more original and stronger form? Is there anything stronger than that we get from the symplectic invariance than we know from volume preservation? Yeah. Right. Okay. So so what is this Poisson structure used for? So we say a function f is invariant under the flow of H exactly if the bracket with the Hamiltonian function is identically 0. So there's a particular, very special class of dynamical systems which have a lot of symmetry. So this is a way of being able to describe inherent symmetries and stronger, as you were asking for, conservation laws. So we say a Hamiltonian system is completely integrable if we happen to find more functions, more observables, which are invariant, just like the energy conservation, preserved momenta, rotational momenta, and all that sort. And if we find n many functions, f1 to fn, on the manifold, which are invariant for the dynamical system given by the Hamiltonian, and which satisfy two properties. First, they should be dynamically independent, which means all their pairwise Poisson bracket should vanish, which means that their associated flows, if we take those functions to generate a dynamical system, those flows would commute. So they generate an n-dimensional commuting system. And of course, they should also be in geometrically general position, geometrically independent, saying that their differentials vanish nowhere, at least on a part of our phase space. And if we have these conditions, then the theorem of Arnold-Liouville tells us in the compact situation. So if we happen to have this, let's say, on an energy level, so a level of H, which is itself compact, then these commuting flows, they generate some n-plane. This n-plane has to close up, and it actually has to close up to be a torus, an abelian n-dimensional group. So in compact case, what we have is we have the phase space, or the part of the phase space where these conditions are met is foliated by n-dimensional H invariant tori. So the typical picture you find in literature is you have sort of a nested family of tori, and on each torus, so I should write this down, use this. So this foliation of this phase space into tori gives rise to better coordinates. We have so-called action angle coordinates. Tau are action coordinates. Theta are angle coordinates on our standard torus, such that the symplectic form can be written in these coordinates. And if we use these coordinates, then the Hamiltonian system on each invariant torus simply looks like a translation. Tau theta is mapped to, so the action variable is invariant. That's the variant, that's the parameter which parameterizes each torus. And in the theta direction, we simply have a linear translation. However, the frequencies, these frequencies, they will in general depend on the action variable tau. So exactly, this is what I said. This is usually only possible on a part of the phase space. Exactly. So my son just showed me this torus yesterday. So I brought one of these tori. So the interesting thing about these tori is we have two qualitative important features. So it depends. So this frequency vector is decisive. If the omega I, the n coordinates of this vector, happen to be rationally independent, then we have dense orbits on these tori. Those tori are the better tori. These tori are the worst you can have. So here we have rational dependence, and they are very flexible. They can easily be destroyed. And this is exactly the driving question where the system came up. So probably the historically most important example is from celestial mechanics. So example, take Kepler's model for planetary motion. So Kepler's model says you have the sun, you have, let's say, n many planets, and if you just consider the sun and one planet, it's rigorously proven from the Newton equation that you have a completely integrable system, which leads to the fact, as we all know, that the planet moves on an ellipse in a fixed plane around the sun in one of those focal points. Now, if you have many planets, then you have to consider the interaction of the planets, the gravitational interaction of the planets with each other, also with the fact that actually the sun is not fixed in one point, but the sun, of course, also wiggles around a little bit depending on the mass of the planet. So if you make the assumption that the mass of sun compared to the planets is comparably infinite, so it's really fixed, and if there is no interaction between planets, then what we have is simply a product of these ellipses. Yeah? It's just like decoupled harmonic oscillators, and clearly we have a completely integrable system. Very simple. So the question then is, if this is the simplified Hamiltonian describing this very simple completely integrable system, what happens if we switch on the correction terms? So if we perturb this. And this is a very hard problem. It's already a very hard problem for three bodies. Already the restricted three-body problem is very complicated, as you certainly have heard a couple of times already from Helmut. And so the driving question is that of stability. Yeah. So long-term behavior. What do we know? Do these orbits, even if we perturb a little bit, stay in a certain bounded region?
Elementary show it's no longer completely integrable.
Exactly. The moment you disturb, you will destroy the complete integrability.
But is it clearly false that it's
Of course, it depends on the disturbance. Yeah, if you add some function, which still Poisson commutes with these n many integrals, of course, it will stay completely integrable. But if you take any sort of generic perturbation, it will immediately be gone. Yeah, so completely integrable systems are very rare. Yeah, they themselves satisfy their own kind of rigidity phenomenon. So you definitely cannot expect to be completely integrable. However, the question is how much of the completely integrable system persists. Yeah, and the geometric way to describe it was to describe it in terms of this foliation of invariant tori. So the question is, how many of these tori might get sort of nonlinearly deformed, but they still exist as tori? Yeah.
Is it possible to give some intuition for why in this theorem you get tori as the invariant?
That comes from the compactness and the commutativity. Well, it's
like, is it obvious it's not a sphere, or?
Well, it's, you see, the two independence conditions give an Rn action on the manifold. So we have a group action. The group is Rn, the additive group Rn, and it's acting on the manifold, and it's a commutative group. So you look at the isotropy group, which gives you a lattice. Yeah. And the compactness tells you, in general, you will have some sort of cylinders times torus, and if it's entirely compact, Rn modulo lattice has to be a torus. That's the argument. Yeah. Okay. So how much of the completely integrable system persists? And this is the question about invariant tori. And this is now, of course, where the story becomes very complicated. This is this famous result by Kolmogorov, Arnold, and Moser, which says that if the perturbation, this term here, is sufficiently small in sufficiently many derivatives. Yeah, and in the beginning it was an outrageous amount of derivatives which was necessary. A 3-digit number of derivatives eventually trickled down, but still it's a unrealistic high number of derivatives you would need to control, and also the smallness parameter. Exactly. Yeah. So, but this is a qualitative statement. If you have this condition, if you have really this smallness of perturbation, then a positive measure set of invariant tori persists. And you can even say which tori want to persist most. It depends on these frequencies. And so in particular, those tori with Diophantine conditions on the frequency. So the Diophantine condition gives you a quantitative way to measure how irrational the frequencies are, and those tori, or the opposite, the tori with rational frequencies, those guys, they will be destroyed the fastest, and the longest what you have persistence is like tori where, for example, the frequency satisfies the this golden ratio. All right. So in particular, this statement says, so you have a positive measure set of invariant subsets, of invariant tori. In particular, this says that this system cannot be ergodic. So this is sort of the important consequence of KM, that it gives you a strong counterexample to the ergodic hypothesis. All right. Okay. So I should come to
Actually's question, but one can show that other things actually answer that. It's irrational.
Stable and unstable manifold fall.
Right, thank you. That's a helpful remark now, because I just wanted to give you one picture. So this is when Poincaré invented his Poincaré section. So of course, if you want to understand things, you would somehow want to simplify. You try to reduce dimension as much as possible, and so on. The more symmetry you have, you use it. And one thing which Poincaré then also did. So this is all about a flow. The Hamiltonian function is not time dependent. And what you can do is, suppose you happen to have a fixed point or periodic orbit, then you can take a surface transverse to this orbit, and you simply look at the return map to this surface. So if you do this and restrict to the energy level of the Hamiltonian, what you get is, from the flow, you come to a symplectic diffeomorphism. Yeah? So the inherent quality of the system guarantees that also this restriction to the surface is still a symplectic map. So suppose now we have a fixed point for such a symplectic diffeomorphism, then the question of stability, at first, of course, you look at the linear algebra. Yeah. So if you have a linear symplectic transformation, one important thing which you see easily is that the spectrum has a certain symmetry. If lambda is an eigenvalue, then also lambda inverse, lambda conjugate, and lambda conjugate inverse have to be eigenvalues. And so in particular, we have seen it's a volume preserving. So the product of all the eigenvalues have to be 1. So that means it's obvious that you will typically have an abundance of hyperbolic fixed points. Yeah, and so we can at most have stability for such a fixed point, means in a neighborhood, or a stability in the sense of Lyapunov orbits which start close to this fixed point, they stay close to this fixed point if the eigenvalues have modulus 1. Yeah, and but it's not a sufficient condition. It's a necessary condition, and but also here we have a KM version of this statement from from Moses' work. We know that if the eigenvalues, if it's elliptic, which is this case of all eigenvalues on the unit circle in a strong way, so let's keep it like this. The strongness in particular means that the eigenvalues have to be rationally independent, satisfy the Fentine condition, and even a bit more than that. Then we have again a positive measure set of invariant tori around this fixed point. That again gives us stability.
So when you first set up this Poincaré slice, you started with the flow on a Symplectic manifold and you're taking a real codimension one slice?
So this is now, so what we do is we first go in the energy level set, which is of codimension 1, 2n minus 1.
Yeah.
We still have a flow in there. And now suppose we know we have a periodic orbit in this codimension 1 hypersurface. Then to that orbit, we take another codimension 1 surface. So this surface will be codimension 2 in the symplectic manifold. And you need a little bit of work to show that the symplectic geometry of the original phase space induces symplectic invariance of this return map.
You just restrict the 2n manifold.
So pseudo A is in 2n minus 2.
Right, so this transverse surface is 2n minus 2. Right. Okay, I just wanted to show you this picture to mention these eigenvalues. Yeah? So these eigenvalues are always applied to a map and not to a flow. Okay, so let's now come to Poincaré recurrence. So recall that the flow, or if we take the time 1 map, preserves omega. So it also preserves volume. Once we have volume preservation, we can go in a much more general context. If we have a measure space X with some measure mu and phi preserves the measure mu, then if the entire space has finite measure, then we have Poincaré recurrence in several different formulations. For example, for every measurable set A and for almost every x in that given set, we have that this point returns to the a priori given set A for infinitely many k. That's one version. Or another version is for almost every point in X, there exists a sequence, an infinite sequence, such that the images under these iterations will come arbitrarily close to this point X. Of course, different points, yeah, I mean, what happens in between, yeah, this is just a selection, and there's not much we can say about what kind of sequence this is. Yeah? So for the times in between, it can do very wild things. And we're just saying that it will return arbitrarily close, arbitrarily often. So question. If phi comes from a symplectic map, so what more do we know? What more do we know? Yeah, so we are throwing away a lot of things. Yeah, we're throwing away that not only the n-fold power of omega is preserved, all the other powers in between are also preserved. Maybe they give more than that. So this question should be seen in the context of symplectic rigidity. So sometime in the 80s, bless you. So let's rephrase this question. What distinguishes symplectic dynamics in terms of Poincaré recurrence from volume-preserving dynamics? So sometime in the 80s, Gromov formulated the following alternative. One of the two things should be true. Either the group of diffeomorphisms which on a given symplectic manifold preserve the symplectic structure within the group of volume preserving diffeomorphisms is C0 dense. This would be termed flexibility, which means that symplectic geometry would behave in a very flexible way. Every volume preserving diffeomorphism can be approximate by symplectic geometry. There's no inherent extra quality which prohibits that. Maybe H principle would be a way to do this, or the symplectic group within the volume preserving group, or within the full diffeomorphism group, is C0 closed, because volume preserving in the measure theoretical sense is even weaker than C0. Yeah, so the alternative would be the C0 closure would have to be really a proper subgroup. So this question was answered. So probably the most famous theorem, and also easy to formulate towards that, is the non-squeezing theorem, also due to Gromov.
It's a theorem that one or the other holds.
So this is just an alternative. I'm not giving any argument why this should be an alternative, and I'm not going to motivate this. Yeah, it simply fits into this question. Is there anything which makes us expect that for Poincaré recurrence we could have a stronger statement? Yeah, and
it is a fact that one or the other holds.
Yes, and I'm going to give you the answer. Yeah. So let's
At
some point, no, he first asked that question, I think, and then he later answered it.
Right. I mean, So, for example, if the manifold M is not compact, you have a lot of flexibility for the symplectic structure itself. There are only standard topological conditions which guarantee whether you have a symplectic structure or not. Whereas in the closed case, you have extra invariance, extra rigidity. So this is maybe one reason for potentially having such an alternative. So the answer was given by Gromov from the following fact. If we consider two types of open symplectic submanifolds of the standard space R to N. So take R to N with the standard structure, consider open subsets, which themselves are then considered as symplectic manifolds. Take the 2n-dimensional standard ball of radius R, and take the infinite cylinder spanned by a 2-dimensional, sorry, that's nonsense. Take the infinite cylinder spanned by the 2-dimensional disk cross R to n minus 2, where we consider this. It's crucial how we distribute the variables here. So this is the product of R2s. Yeah? So this means here we have Q1 and P1, and here we have Q2, P2 up to Q and Pn. So the theorem is there exists a symplectic embedding of the ball of radius R1 into the infinite cylinder of 2-dimensional radius R2 if and only if R1 is less or equal than R2. Now, volume-wise, there cannot be any obstruction. And the ball has a finite volume, the cylinder has infinite volume. Any ball can be volume-preservingly be embedded into the cylinder. So this theorem tells us that there has to be an additional obstruction, which is beyond volume preservingness. So one way of sort of formalizing this can be the so-called symplectic capacities. So symplectic capacities associate to each symplectic manifold some non-negative number, possibly infinity, such that they are monotone under embeddings. They are normalized. They have a conformal behavior if we rescale omega. And the essential part, the really non-trivial part, is that the symplectic capacity of the 2n ball of radius r and the capacity of this cylinder, they coincide and are equal to pi r squared. This is one possible normalization. So these capacities have been studied a lot by Helmut, together with Eddie Zehnder, with Ivar Ekeland. One possible definition of such a capacity follows immediately from the non-squeezing theorem. Say the Gromov width of a given manifold is the largest possible pi r squared, such that you can symplectically embed a ball into that. Actually, the existence of such a symplectic capacity is equivalent to the non-squeezing theorem. So from this non-squeezing theorem, it's a non-trivial proof, which I'll not give. This C0 closeness follows. Yeah, so it's sort of intuitively maybe understandable that these capacities, which sort of formally might remind you to something like a measure, behave much more nicely in this larger category of C0 maps. So you can approximate in C0 and still keep knowledge about the capacities. So one can show that if you have symplectic capacities and you have a map which preserves the value of those capacities on a sufficiently spanning set, let's take linear ellipsoids are a good set, then immediately you can deduce that you have this C0 rigidity. However, those capacities lack one important feature which we would need in order to apply them to Poincaré recurrence. You might think now, if they look like a measure, you would like to try to the same argument. However, symplectic capacities are, at least those which are known, are not additive. And that's a crucial feature of a measure. So you cannot deduce Poincaré recurrence directly from them. I'm not saying that there is no capacity which is not additive, but as far as I know, there's none known. Okay, so now I want to come to the final part. I want to state what kind of extra feature I claim exists beyond the classical Poincaré recurrence. So let me mention one more statement which belongs into this context. This theorem, this non-squeezing theorem, is also called one of the theorems of so-called symplectic rigidity, and that's this whole family of phenomena. And another feature of symplectic rigidity is that of Lagrangian intersection rigidity. So what is that? We say an middle dimensional manifold, an n-dimensional manifold, which has exactly dimension equals codimension in our 2n-dimensional space, L, is called a Lagrangian submanifold if the symplectic form restricted to its tangent bundle is identically zero. Yeah, so they are sort of symplectically completely orthogonal to themselves. The richest source for Lagrangian, or the easiest source for Lagrangian, is certainly again the cotangent bundle. If we take the cotangent bundle with its standard symplectic structure, D of PDQ, then we can easily see that every graph of a closed one form on Q, section in the cotangent bundle, is automatically a Lagrangian. So what is meant by Lagrangian intersection rigidity? Following a theorem, and this is just a simple version of a whole family of theorems. Suppose we have a Hamiltonian diffeomorphism. So Hamiltonian diffeomorphism means it's a symplectic diffeomorphism isotopic to the identity. But the isotope is generated by a time-dependent Hamiltonian function. If we have a Hamiltonian diffeomorphism and a Lagrangian in M, such that, and this is now a very strong condition, there are certainly lots of wide generalizations of that. Suppose that the relative second homotopy group is trivial. That means there is no disk in M with boundary on L which is homotopically non-trivial. In particular, the first fundamental group of L injects. Then there is no way we can displace such a Lagrangian from itself with a Hamiltonian isotopy. Or in other words, there will always be intersections of L with its image. And we can even say how many at least. So the number of intersections is at least given by the dimension of the homology of L. So this is one form of... Excuse me? Thank you. Yeah. this statement about the generic condition. So assume that there's a transverse intersection, and then we must have at least as many intersection points as the dimension of L. And this is also, sorry, in the case where I should have said M is compact. Okay. However, however, if we take, so now let's come to symplectic Poincaré recurrence. What could be one statement? Consider a symplectic ball in our given symplectic manifold. So by the theorem of Darboux, symplectic manifolds always locally are diffeomorphic to the standard symplectic vector space Rn, which says that there are no local invariants, and locally all symplectic manifolds look like Rn, so we always find such balls. So within these balls, there are plenty of Lagrangian submanifolds. For example, we can take Tn, standard torus. Let's take torus of n different radii. Let's take the boundary of n different disks and the product of them. Yeah, in each symplectic plane in R2n. So we have lots of those tori. This theorem doesn't apply to them, because those tori are completely the opposite from those here. You know, the fundamental group is completely killed. They are entirely compressible, and it's very easy to see if you have any symplectomorphism, regardless of Hamiltonian or not, which if it's not identity, it moves at least one point. Yeah, from continuity, it means it will displace definitely some small ball, and in that small ball you find a lot of Lagrangian tori. However, I claim, so I don't want to call it a theorem yet because I still have to finish writing the paper. I claim that if those radii are all the same, and I hope this is just a technical condition yet, then for all symplectic diffeomorphisms, regardless of whether they're Hamiltonian or not, there exist infinitely many integers such that the image of such a torus, which is of this special form, intersects. So why could one expect such a statement? So from standard Poincaré recurrence, remember, standard Poincaré recurrence in particular tells us if we take some ball, we will find infinitely many iterations such that the image of the ball will intersect again. So if so since phi is also continuous, this has to, and it's volume, it's volume preserving. This has to be true also for the boundary, because it's volume preserving. Also the boundaries have to intersect. So those boundaries are spheres of codimension 1. This intersection set in the generic situation, if we happen to have a transverse intersection, would have to be of codimension 2. So it's still a fairly large set. So you could expect that maybe within the boundary you find subsets so that they still intersect. And a possible kind of submanifolds for which this could be possible, just for dimensional reasons, are Lagrangians. Yeah, Lagrangian being n-dimensional submanifold. If they intersect, generically they intersect in points. But so why should this be true? So let me, maybe that's the last thing I want to say.
Recurrence is basically the pigeonhole.
Exactly.
It's
Exactly. You want.
what's your argument?
Right. So I have to resort to Poincaré recurrence somehow. So the argument is, if I have such a Lagrangian, which is of this type of a torus, I will be able to find a polydisk spanned by this Lagrangian. This is where I will use the same technique like Gromov pseudo-holomorphic curves. And in fact, these polydisks, they come parameterized. I can give myself any kind of omega compatible almost complex structure, and this will be important that I have this kind of flexibility. So associated to any j, my given torus will span some polydisk, and the volume of this polydisk is known. The volume of this guy is pi n r to n, and then maybe some n factorial. No, actually, this is exactly the volume. So just from pigeonhole principle, I know that the polydisk will intersect. So what I have to prove, this is the idea, that if the image of such a torus, if I take the polydisk of the image, if that intersects the polydisk of the original torus, then I hope also the tori have to intersect. This is where the symplectic rigidity enters. And so this I can prove in the monotone case. It's wrong. It's wrong in the non-monotone case. Already in complex dimension 2, if I take a non-monotone torus of two different radii, I can just rotate it with an element from SU2, which is Hamiltonian. The polydisk will definitely intersect. It's linear. 0 is in there, but the tori are displaced. However, if I continue rotating, because I still want to prove just recurrence, eventually they will intersect infinitely many times. And right now I'm trying to prove that that is enough also for the non-monotone tori to deduce this. Okay, so this is something which is work in progress. I will eventually talk in the symplectic geometry seminar about that. Thank you for your attention.